And just like I said, I promised I will be writing now the postulates of quantum mechanics, which you will be studying in your quantum mechanics class, but I am going to relate it with what we are doing here in linear algebra. Postulates of QM. The first postulated, at any time t, let's see, at time t, a state of the system or the physical system, even particle, you can write, is defined by a ket or a vector psi t lying in Hilbert space. So now you are getting into, so this is the post graduation. What is this guy psi t? This is nothing but a vector in Hilbert space. What is Hilbert space? It is nothing but a complete complex inner product space. How is it related with physics? State of the system, state of a particle is completely defined by this vector psi t. In classical mechanics, how are you defining the state of the system at given time? Classical mechanics?
Using X and P.
X and P.
So, right, in classical mechanics, please see that you were using xt and pt to completely define the state. By this time, I hope you have already done at least the basics of the phase space, which is Euler-Lagrange equations. I mean, what have you written? Hamilton equations? Yes, no? By this time?
So
Sir,
we
Lagrange
are
equations.
starting
We have started.
Hamiltonian today.
Oh, you are starting. So that means Lagrangian approach is over.
Yes, sir, approx over.
Okay,
Yes,
that's
sir.
good. That's good. That means you also know the dynamics here. But okay, continue with our postulates of quantum mechanics. So time t, state of the system is defined by this xi t. Now, what is this xi t? This is a vector in Hilbert space. Interesting. Not only that, observables or dynamic observables, whatever you call, they are represented by self-adjoint linear operators. Okay, so now you see the importance why we were defining the operators on this space. So we defined what? We defined linear vector space, we defined complex inner product or the inner product, and we defined the operators. So everything is now making sense that observables are represented by linear operators, which means whenever I am making a measurement on a particle, you can understand what we are doing here, that we are operating A on some psi t. That's it. That's it. That's what we are saying the measurement. This is interesting maths. Now, what are the further important points? Only possible result of a measurement of quantity or physical quantity A corresponding to operator A, of course, is only possible value result of the measurement. So if we are going to make a measurement on a particle, let's say position on this particle or momentum of this particle, then the only possible result of a measurement of that quantity is,
A unique real number.
no, not only that, it's much more rigorous than that. Is eigen value of A. Remember, we did this diagonalization and eigenvalue problem. Here, why were we doing it? Because the only possible result of a measurement of a quantity A, which corresponds to this operator, is one of the eigenvalues of that operator. Nothing else is possible. So if you are going to measure X operator or position on psi t, the only possible result will be one of the eigenvalue. That is why it is very important to solve my eigenvalue problem. When I am making measurement on momentum, now think about it. We replace, so P is replaced by an operator P minus IH cross D over dx. Only possible result is one of the eigenvalue of this. And that's why it is so important to get the eigenvalue problem. That is the only possibility. In fact, this goes further. Not only that I know that the only possible is the eigenvalue, but I also know that probability of getting a given eigenvalue, which means one of the measurement, and I just limit myself to non-degenerate discrete spectrum. Okay, it doesn't matter. In quantum mechanics, you will be even explaining further, but probability of getting a given eigenvalue is also given. And that is, somebody knows it, what it is? No?
Sir, mod alpha 1 square.
Mod alpha lambda square.
Yes, sir.
This is interesting. By the way, we wrote mod alpha lambda as just now E lambda comma xi square in the orthonormal basis. Yeah. So I'll just give you a quick look on that because you do not know it. So let me just write down. I even know what will be state of the system after a measurement. So I am doing last three of those. Now, if you look into it, so one was simple that okay, I am representing my particle by state this vectors I. Then 2, 3, 4, and 5, 2, 3, and 4. 2 is that observables, they are represented by Hermitian operators. Third is when I'm going to make a measurement of this observable, then I'm going to certainly get the eigenvalue of that operator. This is why the eigenvalue problems were done. And not only that, I'm saying probability of getting a given eigenvalue. That is given by this. I will explain it in tomorrow's class a little bit on that. And I even know what will be the state of the system after a measurement. Before the system measurement, I do not know whether the state is confirmed or not. But after the measurement, I also know the state of the measurement. And this is something interesting. And I should write down, I mean, I want to first write down all of my postulates. And then I can also tell you this is time evolution of my state. It's okay, the state of the system. Psi t is given by, so H operator I. This is of course, since it is time evolution, it is also given by another, nothing but an operator. So these are the 6 postulates. The question may come more on 2, 3, 4, and 5. 6 is rather simple. I mean, this is the time evolution is given by an operator, which is nothing but IH cross D over dt. So what should we do? I should quickly give you a glimpse and then help you. With your help, I will finish it off tomorrow. Okay. So let's say, consider a particle. I am just trying to explain what I said. And I am giving you a hint and then you are going to work on it. Let's say there exists a particle, and since it's a particle, it's given by a state. Yeah, I want to make a measurement. Just like I said, it is only represented by an Hermitian operator, and this Hermitian operator will have, let's say, certain eigen functions. So this is what the eigenvalue equation. So for the time being, we are just saying, okay, these are discrete ones. Yeah. So now what I say that if I am going to make a measurement of H on xi t, which is the state of the system, then guarantee it is that I will get as the result one of the eigenvalue. This is the guaranteed result, one of it. There cannot be anything else. This is one. Two, I even know what is the probability of getting each of these eigenvalues. And this I am saying that this is nothing but, okay, since I have written phi k comma psi square. And not only that, I am also saying that after the measurement, so this is the measurement. After the measurement, the system, the particle which was in the state psi t will be actually in this state. So after this measurement, and I got this value lambda k, system will be in this one. So when I'm going to make a measurement, I am going to disturb that system. This doesn't happen in classical mechanics. Classical mechanics, you make a measurement, system remains same. In quantum mechanics, you are making a measurement, and what happens that you know that after the measurement, this is the system. Can you understand it from the linear algebra point? So all you are going to do is that this psi t should be expanded in the basis of phi n. Remember, you can use phi n to be the basis for this particle or for that any vector. Why? Because the operator is Hermitian. Eigenvectors of the Hermitian operators are always linearly independent. They are orthogonal. Yeah. So if that is case, then psi t can always be expanded in terms of phi n, and rest everything follows from there. So rest everything follows from there. So please see that I will take this slide as the starting point tomorrow. You understand what is supposed to be done, or you understand the postulates?
Yes, sir.
Yes, sir.
That not only that I know what will be the value which I am going to get. So that value may not be certain value. Each value, it is certain that one of the values I will get, and each value will have its own probability related with it. And also I know that the system will be disturbed and the system will be found in this new state after the measurement is complete. So these are the three interesting ones which I put together in terms of two. I mean, if you look into my postulates, I'll make these ones. So this was 2, this was my 3, this was my 4, and this is my 5. This is the postulates of quantum mechanics. This is why we are doing our linear algebra. This guy is staying in my Hilbert space. Measurements are nothing but the Hermitian operators acting on those states. And by understanding my linear algebra, I know everything of this. And this came from the famous Dirac and von Neumann. Any urgent question which you want to ask? Because I will just say a little bit about it in the next class also.
So, so,
Yes, speak
so
out.
how Dirac delta, Kronecker delta, and Levi-Strauss tensor are different from each other? Like
Oh,
I know
they're
their
totally
definitions,
different, right?
but uh, in
They're totally different,
in
right? I mean,
quantum mechanics,
yes. I mean, one is a tensor
like
of
in
Frank.
quantum mechanics,
Yes.
um, in angular momentum algebra definition, we have used Levi-Strauss tensor.
Levi-Strauss,
Why
right?
not? Why not Dirac delta or Kronecker delta?
Oh, that becomes rather simple for you to understand as soon as you understand the okay. See, whenever you are talking about En comma Em, right? You are talking about only these two, and these two are discrete. Then you talk about what? Kronecker delta, right? But if I say that these are continuous, lambda and mu, so I say instead of nm, lambda mu, but n and lambda are not lambda and mu are not discrete, but they are continuous. Then you cannot use your Dirac delta. Oh, sorry, Kronecker delta, right? Because it cannot be. Lambda is a real number, and n is an integer. So you will have to use something counterpart of that. So Dirac delta and Kronecker delta, you should be clear in terms of the spectrum which you are using. Is it on the integers or is it on the real numbers? Sure. Do you get that point? You get the point? No.
Yes, sir. Yes, sir.
I mean, this guy is just Kronecker delta is easiest of all because it is 1 for n is. This is something which we are giving something like this, right? By Dirac delta, we will come up with whenever the lambdas or whatever the subscripts are, they are continuous. So that's pretty simple. What you are saying as the Levi-Civita, that will come with when you are going to do something like sigma I, sigma j, where these are the polyspin matrices, and you are going to explain your result in terms of sigma k, which means that suddenly you will start playing with 3 variables such that these 3 variables have some interesting relationship. So up to this point, you are only worried about that whether one vector is, I mean, if you can say orthogonal to another vector. I do not need to care about one vector orthogonality with 2 vectors simultaneously. I know this is orthogonal with M, N is orthogonal with P, M is orthogonal with P. That is sufficient for me, and hence my Kronecker delta comes. Here the continuous variables, my real variables or continuous variables, my Dirac delta will come. Whenever I will encounter a situation where there will be 3 of these which are related, there you will get the Levi-Civita, which is what is going to happen in the case of spin angular momentum or the orbital angular momentum. And there you will have Levi-Civita symbol, but in some sense you are doing some sort of a tensorial things. I mean, you understand a little bit of the tensor? The rank 1, rank 2, rank 3. When I'm saying a vector,
Yes, sir.
what is it in terms of a tensor? When I'm saying vector,
Rank
three-dimensional vector. Rank 2 or 3?
2, sir.
2. And how do you say that?
Two. Two.
And how do you say that? That it is of rank 2, a 3-dimensional vector?
Sir, I only remember his scalar is
Okay.
rank.
Okay, so
Exactly.
I won't go into the details of that, but please understand that the
Same.
question which you are asking, this is Kronecker delta, this is Dirac delta, and here, these are the spin matrices for the spin angular momentum I wrote, but the same thing you can write down for Lx and Ly, which are the orbital angular momentum. There it will come. Fine. So, okay, I mean, this is beyond what we are doing at least at the present. So, I'll take up this question also at some point of time when we will be doing group theory. There I will introduce the Levi-Civita.
Okay, sir.
Okay, I have another class and you guys also have another class. So
Okay, sir.
thank you guys, and we will build on to this discussion. So we will conclude it tomorrow, that means.
Sir, we will not have the class today.
Oh, sorry. I have my students JRF to SRF seminar. I should write it down. I will write it down there. Fine. I will write down on the group that today we will not have it. In future, we will again have it.
Thank you, sir.
Yeah,
Okay, sir.
thank you.
Thanks.
Thank you, sir.
Yeah.
Yes, sir.
Thank you, sir. Thank you, sir.
Thank you
Thank you,
guys.
Thank you, sir.
Right.
Sir, I have a doubt.